Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work. For this particular problem, we want to determine the angle theta for equilibrium. We will apply the virtual work equation to solve this problem by determining the virtual work due to the weight of the ball, that due to the weight of the table, as well as the virtual work due to the two springs, summing them together and solving the equations to get theta, which is that angle we are looking for. So this is the table, and we have the ball with its center of gravity here acting downward. Let's call the weight of the ball W1, and we have the table. Let's call its weight W2 acting downward. Of course, we have the two linkages. Okay, okay, let's call this A from B, and of course there's an angle here, theta. It's an angle here, theta. Okay, all right. Now there's a distance between this point and the top of the linkages and the bottom of the table. Let's call that distance small distance b, and also the distance between here we have the center of gravity of the ball and the top of the table. Let's call it u. All right. Of course, we have a spring here. Okay, let's call, they've given, we are given this distance. Okay, and we are given the length of each of the linkages. They are equal. All right. So the force acting, the spring force, let's call it F, and of course it's going to have a virtual displacement acting that way. Let's call it the X. So the virtual work is basically negative. Okay, and for this one we are going to have a virtual displacement this way. Let's call it y subscript one, the y subscript one, and for this one you can see that the virtual work here, the virtual displacement for the two, for W subject one and W subject two, they are opposing their respective or the weights. W1 and W2 are opposing their respective virtual displacement. So we are going to have negative uh, virtual work for each of them. All right. So we can just look for the spring. We know that the spring is equal to get the force of the spring is the stiffness times the displacement. Okay, and if we do that, we can get our displacement, which we can just determine the position coordinate, fixing or specifying f to be 0.25, okay, cos theta. Okay, of course we know that the length of each of the linkages there, a, b, and let's just, okay, so this is AB and this is C D. Each of them is 250 mm, which is 0.25, which I've used converted to meter. Okay, in meter 0.25. All right, so we have that. So if we take the derivative, we're going to have this, okay, with respect to theta, we'll have this, which is going to give us equal to minus 0.25 sine theta. Okay, now having done this, we can just make this the sorry to the formula. Have this is going to give us minus 0.25 sine theta d theta. So that for that. Then we can also look for the 1IB weight. We're going to have which is sorry, the one for W1, okay, which has a mass, the bowl has a mass of 1 kg. So we can also determine the position coordinates. So let's call it y substitute 1. It's going to give us equal to 0.25 sine theta. Sine theta. Now you can see that to get the total vertical distance, we need to add that distance u. Okay, so we're going to have that so that when we do our differentiation, we're going to have this with respect to theta. It's going to give us 0.25 cos theta. Okay, so that's what we are going to have there. So we can proceed and just get what the y substitute 1 will give us. So it's going to give us 0.25 cos theta d theta. Right. Now we can also go consider the 5 kg mass, which is our W2. So if we do that, we are going to have, for that one, we are going to have the position coordinate specifying W2, let's call it y subscript 2. So it's going to give us 0.25, okay, which is the length of the linkages we have there. Each linkage has a length of 0.25 meters, which is similar as 250, that similar as 250 sine theta. So we are going to have this. This is what we are going to have. Okay. Now we are going to add our v to it to get the total vertical distance. That small distance there that we defined the other time, we indicated, okay, under the table, between under the table and the link and the top of the linkage. All right. So if we now do this, take the derivative with respect to theta, we are going to have it to be 0.25, 0.25, 0.25 cos theta, 0.25 cos theta. All right. Then we can look for what this will give us. It will give us 0.25 cos theta d theta. Okay. Now we can now apply our virtual work relation. Okay. So if we bring it in, we know that du is equal to 0, the virtual work. So let's consider the spring. For the spring, we are going to have, of course, we know that the virtual work there is negative, but the springs, there are two springs, okay? One on one side, one on the other side. So, and the spring is F, the X, okay? That's the, the virtual work there. That will consider also the, sorry, we consider the weight W1. So it's going to give us this. Okay, and for the W2 or W subscript 2, the other one is W subscript 1. You're going to have this, equate it to 0. All right, we can plug in values into these into the equation. If we do that, we're going to have these to be equal to, for the spring, going to give us 2 minus 2. And of course, we know that 2, the fx or f is the same thing as k, the spring stiffness. Okay, times x. Okay, so is the spring stiffness times x, that is f. Okay, then we have the x there. So I just want us to have this in mind. Okay, for this particular one here. Okay, this quantity that is here, this part. All right, so if we know that, let's just plug in values. So we are going to have plug in values. We'll have minus this. Okay, putting in the spring constant, which is minus, which is 200. We're going to have this 200. Okay, times our x, which is 0.25 cos theta, 0.25 cos theta. Okay, all right, times the x, which is 0.25 cos sin theta, the theta, 0.25 sin theta, the theta. Okay, so you have that for that. All right, please, there's a negative sign. This one is negative, minus 0.25 sin theta, the theta. All right, then we also come for the other parts. For w1, we're going to have it to be minus, okay, 1 times 9.81, okay, times 0.25, okay, cos theta, the theta, cos theta, the theta, okay. Then we're also going to have for the 5, or for W2 rather, is going to give us 5 times 9.81 times 0.25 cos theta, the theta. Okay, you can see that theta will be common. The theta will be common among them. You can just bring the theta out. You're going to arrive at 25 cos theta sin theta, cos theta sin theta. Okay, minus 14.71 cos theta is theta. Okay, it's equal to 0. So if we solve this, we are going to arrive at, no, as a matter of fact, you can see that cos theta is even common among them. So we can just bring that cos theta out as well. Okay, if we bring out cos, bring it out, we're going to arrive at cos, the cos theta is common here, as you can see. So if we bring it out, just bring it out and solve the problem. Okay, we are going to arrive at cos theta. Okay, to be equal to 0 degrees. Okay, and of course, sorry, this is cos theta. You're going to have cos theta to be equal to 0. Therefore, theta is going to give you 90 degrees. Okay, then you also have 14 sin theta, sin theta. Okay, to be equal to 14.71 over 25. So if you take the arctan, you are going to arrive at theta. If you take the arc sine, you are going to arrive at theta to be equal to 36.04 degree. So these are the angles, 90 degrees and 36.04.